Hey folks, so after the last 10 videos or so, we've been through all the different implementations necessary for using BSTs to implement symbol tables. So what do we get out of this, right? What is the end result at the end of this day? Well, we have a new data structure implementation, right, that can solve this problem with symbol tables. So initially, right, in the first module, we talked about using arrays, we talked about using lists, and we got some pretty good performance from that. Well, we got good as in it's at least linear time, right, but we hope to get better than that. So this is what we had in the past, right, basically these two over here. So that, that's fine, that's great. And now, right, today, right, we've done all this implementation, right, of this tree. And we also spoke a little bit about basically the structure of trees, right? We had this discussion where it's like, well, if I want to know how much work it takes for a put to run or get to run, basically what I ask is how many comparisons are needed, how many different nodes does it need to look at, and how many nodes does it need to look at before it gets to the one that it actually, needs, right? The one's being asked for. And depending on how a tree looks, it could be really bad or really, good, right? Depending on whether it's a stilted tree or it's a balanced tree. We had the discussion, and so in the end, though, what we ended up deciding is, hey, the thing that's most important for us, right, is to look at that average case, right, or that typical case of where I just have a bunch of things kind of thrown into my tree in some sort of random order, how long the path is going to be there. Now, there is a proof, right, we didn't do it, we just jumped kind of straight to the result, and the result was what you see up on the screen, right, so 0.139 is how many comparisons it'll need, right, for us to basically get from, the root of a tree to some child, right? If I'm looking up, this particular node, right, in there where I'm doing some sort of a get, right, it'll take me 1.39 log n, right? N is obviously the number of nodes in the tree. So it's a little bit of work, right? It's a little bit of work. Particularly, right, what you might notice is that this over here is not as good performance as this over here, right? So we had basically log n, right, for our binary search, versus now we have 1.3 log n. And at first you'd be like, well, that's a little bit bad, but look at it this way. Over here, you went from linear time to logarithmic time, okay? So that's nice, right? So we basically have log time versus log time and linear time, okay? So in terms of big O, it's clearly better. And we get, of course, our ordered operations. So right now, right, life is looking pretty good. We do have definitely a fast way to implement this thing. Now in the future, we're actually gonna have an even better way though. We're going to have what is called the hash table, which uses a hashing scheme to store indices inside of an array. Basically, there's a bunch of magic that happens that can map this arbitrary key to a particular space in an index, to a particular index in an array. And when we do that, right, when we finally get down to our hash table implementation, what we'll have is approximately constant time. So here I would we'll put 1. We'll put tilde of 1. It's not strictly correct, but just, because it helps the motor race a little bit, we know that we're going to get down there to constant time, right? So in terms of big O, right, big O, we basically had, this is big O of n, big O of n, big O of log n, big O of n, right, and then this was big O of log n. Then we have the bottom, then we have the bottom row, which is big O of log n, and again, big O of log n. And then what we're proposing, right, is eventually we'll get to this, big O of 1, big O of 1. So that's where we're headed, right? That's going to be in a future module. For now, though, we've already done a pretty good job making things faster with binary search trees. So yeah, binary search trees, they're kind of neat, right? They're kind of a new way to structure data, right? It's kind of very clear that just kind of the way we order things, right, gives us a lot of leverage in terms of running algorithms to be able to find things.